and to introduce Naomi Leonard, who is today's speaker. As many of you know, Science Sundays is a joint project of the College of Arts and Sciences here at Ohio State and of 8 research institutes in the college. For those of us who help organize Science Sundays, today's event is a little bit unusual. This is the first time in the 8 years of Science Sundays that one speaker has been nominated to talk from 2 different institutes simultaneously. The 2 centers are the Mathematical Biosciences Institute, of which I'm associated to, and the Advanced Computing Center for the Arts and Design. The mission of ACAD is to educate, inform, and inspire innovative thinking and experimentation in the area of arts and technology through collaborative academic and research experiences. MBI, on the other hand, fosters the application of mathematical, statistical, and computational methods in problems in the biosciences. This is what we call math to bio, and the development of new areas in the mathematical sciences motivated by questions in the biosciences, bio to math. And now for today's speaker, Naomi Leonard is the Edwin S. Wilsey Professor of Mechanical and Aerospace Engineering and a faculty member in the program of Applied and Computational Mathematics at Princeton University. Leonard's research field is control and dynamical systems. The field involves designing and analyzing the behavior of complex systems. In recent years, she has focused on multi-agent systems in engineering, the design of robotic teams, in nature, the joint movement of animal and human groups, and in mathematics, developing approaches for leveraging insight across contexts. Naomi has collaborated with biologists to help explain the collective dynamics of animal groups and to help explain decision-making under uncertainty. In 2010, she co-created Flock Logic, an art-making project that explores what happens when dancers carry out the mathematical rules for dynamic response used to model flocking birds. Naomi Leonard has received many prizes and awards for her work. I'll mention just 2. She is a member of the American Academy of Arts and Sciences and a MacArthur Fellow. The title of her talk today is Flock Logic, the Art and Engineering of How Groups Move. Naomi?
Thanks very much, Marty, for the introduction, and thanks to you all for coming out, or maybe coming in, despite the beautiful weather outside. So I have 3 main goals today as I talk to you about the art and engineering of how groups move. My first goal is to give you insight into how the complex and marvelous motion of a group can emerge from a collection of individuals. And my second goal is to show you how it's possible and why it's so illuminating to study the collective motion of groups in nature, in robotics, and in art as part of the same story. And my third goal is to impress upon you the role of feedback in all of this. And by feedback, what I mean is the responsive decision-making of individuals and how mathematical models and methods can be used to formalize a unified investigation of collective motion. So by a group, I'm referring to a collection of individuals, and let's call them agents, where each agent can independently move itself around, and each agent can sense its local environment. So this might be something about the external world, but it also could be something about what its neighbors are doing and how they're moving. And finally, this agent can make its own decisions about how it's going to respond to what it senses. So by that definition, certainly animal groups are these kinds of groups, like this school of fish, which I'll show you in a moment, where each individual animal or fish can certainly move around on its own. The fish can swim. And each individual can sense, so these fish can sense their local environment, they can sense some of the other fish nearby through vision, olfaction, through their lateral line where they measure local pressure. And these fish can make their own decisions, certainly, about how they're going to respond to what they sense. And the kinds of questions that we ask then are, what are the individual decision makings? What are the interactions among the individuals that lead to these remarkable collective behaviors that we observe? For instance, how is it that these groups can move seemingly so stably in these beautiful patterns despite all the pushings and pullings of the current, despite all the uncertainty in the ocean, and at the same time be very sensitive when something in the environment changes and they actually have to change and be flexible. For instance, how is it that they have somehow managed to respond to whatever happened in the environment that made them move from the circular motion gracefully into the polarized motion? And furthermore, how do they do this despite the fact that each individual has limitations on what they can sense or what they can communicate or what they can even compute? So at the same time, this definition of a group could refer to a group of robotic agents. So in this case, I would imagine that each robotic agent has some actuators on board so that it can move around. It could walk if it were a legged robot. It could swim if it's an underwater robot. It could fly if it was an aerial robot. It would have to be equipped with sensors so that it could measure its environment and also measure something about the movement of its neighbors nearby. And also would have a computer on board so that it could make those decisions about how to respond in response to what it's sensing. So here we have a very parallel kind of question. In the animal groups, we're trying to explain what we observe at the level of the group by understanding or by investigating what the individuals might be doing. Here, the question is, how do we prescribe those rules, those strategies for individuals on what they should do in response to what they measure, so that at the level of the group, they move in patterns that are stable but also flexible, despite all the incredible uncertainties in like an ocean environment, and yet also be flexible when interesting things or compelling things change in the environment. So what I'm showing you here in this video is an animation of a project that I worked on with colleagues in oceanography and ecology, where we collaborated to use a team of robots in the ocean to move in patterns that were efficient for collecting data, both about the physics, like temperature and salinity and currents, and also about the biology, so concentrations of phytoplankton, for instance, and how we might use these data, ultimately, to help us understand things like the ecosystem or the effect of phytoplankton on climate change. And so you'll see, this is an experiment that we carried out. This is vehicles moving in and around Monterey Bay. And so the vehicles moved around in order to collect data for this purpose. And our goal, again, was to make sure that they were able to do this in a stable and flexible manner. So likewise, we can think about a collaboration of artists, for example, dancers, as a group, according to my definition, because certainly each dancer can move around on its own. Each dancer, in fact, is trained to be highly aware of what's going around in their local environment. And of course, each dancer can make decisions about how he or she's going to respond to what they sense. So here are the questions for us were, how do we design performance instructions, rules for improvisation, so that a collaboration, a group of dancers might shape in an improvisation a dance piece that was beautiful or provocative or compelling in some way. And this is an example, I'll show you in a second, a video of a project with my colleague Susan Marshall, who's a choreographer. This is what we call a performance event. The project was called actually Flock Logic. So this was back in 2010, where we worked with a group of professional dancers as well as a group of students. So this was through rehearsals with the dancers and actually through a course that we jointly taught at Princeton with the students to explore what happens when both highly trained dancers and ordinary human movers like us employ the rules, the flocking-like rules that we use to model flocking behavior or schooling behavior. So our goal through those rehearsals was to understand how to shape those rules and performance instructions so that we would see beautiful patterns both spatially and temporally. And let me just show you a little clip from this. So it starts with a combination of the dancers and students, and then they soon bring in some of the audience who had sort of volunteered to be part of the, and here they come. But what you'll see are these kind of circular motions and these polarized motions that you see emerging in the fish schools. So, in addition to thinking about how groups move together and in these spatial and temporal patterns, sort of underlying this is also how groups decide together. So it's one thing to say we're all going to move together, but which way are we going to move? Are we going to go to the right? Are we going to go to the left? So we also think sort of at the same time about what does it mean for groups to decide together? And we can think about this again in nature. So for instance, this herd of zebra have to decide how they're going to respond to a threat. In this case, it's actually a robotic lion that my student in Kenya drove towards these zebra. Not very scary, but enough to get them to sort of run away. But they're deciding, where should we go? How should we stick together and yet evade this scary thing? The top right picture is a picture of some desert harvester ants who have to decide whether or not they should go out and forage for seeds in the desert of Arizona, taking particular care on very hot and dry days. The bottom right is a photograph of honeybees. So this is a snapshot of a honeybee doing something called a waggle dance. So these are house hunting honeybees. They're looking for a new nest site, and they absolutely have to make a choice because they need to pick the best nest site. The fourth picture is of Dunlin birds who are migrating from Alaska. They're at a rest stop on an island, and they have to decide together when they're sated by their food, when they've had enough rest, and so that they all take off together at the same time as they continue on their migration route. But the same kinds of questions we ask in robotics. So, for instance, on the top left are a couple of aerial vehicles who have to decide where and when to drop fire retardant on a forest fire. And on the top right, is a bunch of windmills who have to decide collectively how to reorient themselves as the wind changes, and so they organize their collective orientations to take best advantage of the wind and what's coming off of the nearby windmills. On the bottom left is a couple of creepy crawling robots that are doing maintenance, and they have to coordinate and make decisions about where to go, especially if they have to work collectively on something. And the bottom right is an example of some robots. This is in Italy after an earthquake a few years ago, where you see some wheeled robots and a flying robot that also have to make decisions about where to search at what point in time. And we also study this in art making. So this is a second dance project. It was called There Might Be Others. It was a collaboration that I had with Rebecca Lazier, who's a choreographer at Princeton, and Dan Truman, who's a composer. And here the idea is that it's an open choreographic work where the dancers have choreographic authority. They're able in the moment to make decisions, compositional decisions. They're essentially negotiating among themselves from a vocabulary, sort of a pre-choreographed set of dance modules, when and how and where to do these, kind of in sequence, but also to create beautiful and interesting juxtapositions and relationships and timing. And our idea was to think about this as a decision-making network. How do we understand how to prescribe, again, performance rules and improvisational instructions so that we could shape the decision-making in really interesting and provocative ways and explore ideas like stability and flexibility and what does that mean in an art-making context. So to me, these parallel questions of explaining behavior in nature and designing nature in art or in robotics absolutely suggest a joint synthesis challenge. So in some respects, I'm trying to synthesize dynamics, both to explain the mechanisms that help us understand what's going on in the animal groups, and that allow us to define ways to enable our robots to maybe inherit some of those amazing properties of flexibility and stability. And likewise, to explore what this could mean in art making. What does it mean in terms of aesthetics, in terms of beauty or provocation? And can we think about this in a unified way? Can we use mathematics, actually, to abstract out some of the underlying principles so that one domain can inform the other, so that we can come up with testable hypotheses, go into nature and query the system, run experiments, come back and get new ideas about design, try things in the field, come back and get new ideas about what might be going on in nature or what we might try out in art. So the essential ingredient, as I mentioned in the first opening slide, is feedback. This idea of what does it mean to sort of be aware of your environment, respond to your environment in this kind of continuous way. And so if I think just sort of generically about some system, you can maybe, oh gosh, I'm sorry, I keep doing that. I'm the system, let's say, and I'm trying to walk down the hallway, and the input is, my legs, I can walk, and the output is my trajectory, my path. And if I am in this setting, which we call an open loop system, where I have to plan my path, but I don't get to sense anything, it's like, being blindfolded and wearing, headphones and walking down the hallway. And I'll only do a good job if I know in advance everything. I know perfectly that nobody's going to run across the hall as I'm walking, that I have some, super ability to maintain my direction without kind of drifting off. I probably won't do very well. So what we add is feedback. And feedback is there to regulate my behavior. So I actually look, it's not necessarily conscious, but I'm constantly sort of maybe adjusting as I walk, especially if somebody runs across me, my path. But this feedback is in every regulatory system in our body. It's in the airplanes you fly. It's in your cell phone. anything that has to behave in a way that's reliable has got to have feedback. And feedback essentially has these three ingredients. So something comes into the system, you have a way to change the dynamics, and something comes out. And then you measure. I measure where I am in my path. I determine how I want to adjust it. We call that a feedback rule. And then I act on it. I actually move my body. I steer. And it gets even a little more complicated than that, because things might change, right? Somebody might run across my path, or maybe somebody opens a window and now I want to list a little away from that to keep warm. And so in my rule, there might be parameters that I want to adapt. I want to change as a function of these environmental conditions changing. So the feedback gives me the stability, and this kind of adaptation of my rule gives me my flexibility. This is kind of the underlying ideas. And I can think about this for my fish. So here's my fish with its fins and tail. That's my input. The trajectory is my output. The fish can measure its trajectory or something about it. Its rule is how does it want to adjust its trajectory. And then the way it acts is it turns or accelerates or decelerates. Likewise for a robot. But now instead of fins and wheels, I have fins and tail, I have motors and wheels. And even for the dancer, many more degrees of freedom, right? But so now all the parts of my body, and I look at my path in my limb space, the space of where my arms are, and what I want to do, and I compare that to what I'm actually doing, and I might make adjustments. But now, so I might call each of these complicated systems, but where we get to the real complexity, okay, before I do that, I wanted to give you a little example about this rule. And this is a mundane example, but it's super familiar to those of you who have cruise control in your cars, so I guess most of you. So now think about the car. The gas pedal is the way we can adjust how we move. The speed is what we're going to measure. And suppose you've set your cruise control for 55 miles per hour. The car is measuring its speed. It's comparing what it wants to be, what you want it to be, to what it actually is. So I'm going to call that E. That's the error between the desired speed and the actual speed. And what's my rule? Well, the simplest possible thing is I'm just going to multiply it by some factor. I'm going to call that K1. That's my design parameter. And A here is my acceleration. So K should be positive, because if I'm not going fast enough, the error is going to be a positive number, and I want to accelerate. So I want acceleration to go up. And if I'm going too fast, it's going to be a negative number, so I want acceleration to go down, right? So that's just a little rule that says if I'm not going fast enough, up the acceleration, which translates into the gas pedal going down, right? And feedback is just going to continuously check this and correct for it. Okay, that sounds probably too simple, right? Because things can get way more complicated than that, right? Like, what if you put on your cruise control and it takes forever for it to catch up? You'll be really frustrated. Or what if it overshoots and then you're in trouble and you get a ticket, right? You don't want any of that. You certainly don't want it to be such that the person in the back seat is gonna get nauseous, right? So you don't want it to be really oscillatory, right? We might think about a more complicated rule. We also might think about the fact that this rule has to adapt, like I mentioned, right? So if it's raining, or if I'm going uphill, or if it's a gravelly road, suddenly the rule might have to change as well. So now what happens, as I mentioned before, when it gets more complex, when we have multiple, I've only shown you 3 fish, but look at the complexity. Each one of these guys has their own feedback loop, and they're connected, right? Because what each fish can sense is not just, its own trajectory, but something about at least the relative trajectory of maybe its next door neighbors, right? So what are the rules? So maybe it's things now like I'm going to try to follow my neighbor, because maybe they know that there's some good food over there, or maybe they know that there's a predator. Or I might want to avoid them, right, if I don't want to crash into them, right? So I might want to balance those two kinds of rules, depending upon how close I am to them. Or I want to keep track of what a lot of others are doing. And then I respond by turning or accelerating or decelerating from a fish. And then you can see how things get even more complicated when the environment changes. So we might have stability of these kinds of schooling motions as we move around together. But what if we need to do something in a circle, or what if we need to do a polarized motion? We need to be able to adapt our parameters. And that might also include adapting who I pay attention to, because I might want to pay attention to more, like the second layer of neighbors. Or I might actually move, and now my neighbors might be different if I move relative to some of the other fish. So let's kind of unpack this. This is what I want to unpack, each one of those blocks, okay? So let's talk about sensing first, okay? And let's sort of focus on what it is when I'm thinking about these groups moving together that I really care about. So let's just focus on sensing the relative direction of motion of my neighbors. And this is a photograph of, with a sort of a superposition of these pretty lines from my colleague who studies schooling fish and tries to figure out the visual field of each fish as they move so that he can understand, at least in principle, who can see whom, right? That's these arrows between, that I had between everybody's feedback loops. And certainly who can sense whom is going to affect how we move, right? And these are the kinds of things that we want to understand. Likewise, if we have a group of robotic vehicles like these are these underwater gliders that we used in the ocean in Monterey Bay, they can, in principle, sense one another. Maybe their sensors, if they're optical or they're acoustic, will be limited, so they can only sense ones nearby. And so it's sort of somewhat analogous, right? And the dancers, right? So this is a snapshot from a rehearsal of flock logic in the classroom. And in this moment, because in this setting, the dancers were told to stay arm's length from two others in the group, we could actually back out in every frame of the video who was paying attention to whom. So you see the little arrows now of we can sort of keep track of who is sensing or observing whom. And so there's this block we call sense, and we want to translate it into something that we can encode, because you can see it can get so complicated. And if we want to get any kind of traction on this, if we want to be able to say something about it, if we want to be able to understand what kinds of interactions lead to what kinds of behaviors, or design interactions that lead to desired behaviors, we have to somehow encode it. And so this is an encoding where each, it's actually called a graph. So this is a mathematical structure called a graph. And it's literally that picture that you see where each purple circle represents a fish or a robot or a dancer. And the arrows represent who's sensing whom. So in this picture, dancer number 1 or fish number 1 can observe fish number 4 and fish number 3 and fish number 2. But fish number 3 can't observe fish number 1. You see the arrow is sort of has only one arrowhead, but fish number 3 can observe 2 and 5. Right, so we can encode this, and we actually encode it in an array of numbers like you see here below, and a couple little examples, like we call the complete graph, the one where everybody can see everybody, and we call this cycle, this directed cycle, where 1 can see 4, and 4 can see 3, and 3 can see 2, and 2 can see 1, and we just have a sort of a way of keeping track with these numbers of who is paying attention to whom. And that already gives us some sort of mathematical traction in an encoding. So then comes maybe even the harder part is, how do we then encode the rule? And this is a sort of a typical model that biologists use. So they think of this little goldfish in the center. That would be, every fish would have this rule applied to it, but let's just focus on the goldfish. And the goldfish has these 3 zones. So if it finds anybody within this very close zone, it's going to sort of move away from it. It's going to try to avoid crashing into it. And the larger, the sort of the outer zone, the zone of attraction, that's when it can sense them, but they're a little further than they'd like to be, so they kind of steer their way towards them. And that the middle zone is called the zone of alignment. So this is where they keep track of the direction of these nearby fish, and this is the one I want to focus on today. And they try to align with them, right? So how do we encode this, right? So that's just a picture, and I've told the rule to you in words. So how do we encode this? So let's think about looking down on a group of these guys and assume they're just moving on the floor or on the plane, maybe in shallow water. And I have 3 of these fish or robots or dancers, and I've numbered them. And here, let's assume they're all moving at the same speed, okay? So I really just want to keep track of which way they're heading. So R1 points out the position of the first fish, but theta 1 keeps track of its direction of motion relative to, I don't know, say due east, right? Fish 2 its direction is kept tracked by theta 2, et cetera, right? So what I want to have for the rule for each of these fish, like for fish 1, I want to have a rule that allows it to figure out how it should steer, or how it does steer, in response to measurements of the relative directions of its neighbors. So a relative direction of fish number 2 relative to fish number 1 is just theta 2 minus theta 1, right? So I want a rule for how fish 1 changes its direction. And we do this using this notion of synchrony. So what do I mean by synchrony? So the synchrony of directions would mean everybody moving together. And so there's a very nice formal way to do this. And I'll show you, if you look at the top picture in the top left, this is kind of a nice way to think about it. That's a circle of radius 1. Okay, and for every one of my fish, I've drawn a red arrow that points in the direction that it's moving, right? And I'm taking the average of those red arrows, and I get that black arrow that I'm calling p theta. Okay, so it's the length of that arrow that I call p theta that gives me a measure of the synchrony. So how do I understand this? So if I look at now of these 4 circles, look at the one on the left where I say p theta is equal to 1. So this is everybody moving in the same direction. The average of the same arrow is just the arrow, and the length is 1, right? They're synchronized. But if they were all moving, for every fish moving in one direction, there was a fish moving in the other direction, I would get a picture like here, and the average would all, give me 0. So this would cancel this would cancel this, right? So this p theta would be 0. Those are kind of the 2 extremes. So I could be completely synchronized, or what we call balanced, which is completely anti-synchronized. What's really interesting is that for a group in motion, where these thetas are their directions of motion, when we're synchronized, it corresponds to the group having the maximum speed, everybody moving off at that same common speed. And when their orientations are balanced, and if they're moving around a circle, it corresponds to them moving around the circle and the center of mass of the group not moving, the group not leaving the page. They're just literally, because this guy's going this way and this guy's going this way, et cetera. So this is kind of you might say, well, what does that have to coming up with rules? But this actually gives me a beautiful rule if I think about the fact that all I want to do is figure out steering rules so that if I want them to be synchronized, I just want to maximize this thing. I want to drive p theta to 1. And if I want them to do some kind of circular motion, I want to drive p theta to 0. So we do that using something called a gradient. So what a gradient is precisely, so if we take what's called the gradient of p theta with respect to theta 1, we essentially get fish 1's rule for changing its direction in order to contribute to driving p theta to 1. It will tell it what it should do, or the rule gives it a way to contribute to getting them all synchronized. And we would give fish 2 the gradient of p theta with respect to its direction. And we can generalize this rule using that encoding of who can sense whom, because we don't want a rule that requires one fish to respond to a fish that it can't sense. So we want these rules to be practical in the sense that they take advantage of what's available for measurement. So relative measurements of nearby fish. So let me show you what this rule looks like for fish number 1. So this theta 1 new is its update, where it should turn next. Theta 1 is which way it's heading now. So this gives me the change. And what does it look like? So if you look in the parentheses, it's the sum of all those relative headings, right? And I'm multiplying it by a design parameter that I call k theta. And I'm dividing it by what I call N1, which is just the number of neighbors that fish 1 has plus 1. Okay, so that's just a pretty simple rule. I just add up my relative measurements, and I multiply by some. It's like that K in my cruise control. It's a design parameter. You know, I can adjust the strength of how much I'm gonna turn, and then I also divide by N1. What's interesting is if K theta is positive, this drives P theta to 1, and all I have to do is change the sign. So if K theta is negative, it drives P theta to 0. So with this one simple parameter, I can get synchrony, or I can get this balanced kind of behavior. And if you look at this closely and you set this parameter K theta to equal to 1, and you add theta 1 to both sides of the equation, what the new direction actually looks like is just the average of fish 1's own direction and its neighbor's directions. So the rule only relies on relative measurements, but what it's really doing is just averaging. It's just adjusting so that it keeps trying to move in the average direction of its local neighborhood, which seems quite logical. So let me show you a little example. So here are 3 fish, and I'm going to use the clock. So fish 1, the one that I'm going to focus on, is moving in the direction of 11 o'clock. Fish 2 in the direction of 7 o'clock, and fish 3 in the direction of 6 o'clock. Okay, so what's the rule? I'm just going to average. It's 1/3 of 11 o'clock plus 6 o'clock plus 7 o'clock. That's 1/3 of 24, which just gives me 8. So in this next update on its direction, it should move to 8 o'clock, and this pushes me up this P theta hill. I'm moving up the gradient of P theta. Okay, then I do it again at the next moment. How do I update my direction if I'm fish number 1? Oops, I had it here. So I do the same thing. Now I'm at 8 o'clock, 8 plus 7 plus 6. That gives me 21. I divide by the number of neighbors, which is 2 plus 1, which is 3. That gives me 7. So now I move to 7 o'clock. And you can see I'm moving up the P theta hill. I'm also becoming more synchronized. And here, only fish 1 was doing anything, but in reality, fish 2 was also doing this. So they're much more quickly coming together. And it's with rules like this, with mathematics like this, that we could actually prove things about how fast they come together, what happens when there's uncertainty, these kinds of things. And we can even generalize this further. So remember, I was just looking at that example when K theta was positive, but when K theta is negative, they move around circles. And we can generalize this not only to get them moving around circles, but we can think about extra parameters that allow them to just sort of distinguish in what kind of patterns they move around circles. So here is an example of 12 individuals moving at the same constant speed, starting in the same position and orientations, and using these kinds of rules with just changes in these signs, S-I-G-N, of these parameters. And so you're going to see the top left, they're all going to synchronize so that it's going to look like they're on top of each other. So they're moving around the circle, and they're all in the same direction. In the second one, and the middle one on the top, they're going to move into 2 groups of 6, right? So they're balanced, but it's a particular kind of balancing. In the top right, there's 3 groups of 4, then there's 4 groups of 3, 6 groups of 2, and then 12 groups of 1, right? See, there are all different ways that they can balance. So P theta is now 0, but there's other parameters that we're also using to sort of distinguish in very simple ways these different kinds of patterns. And so we can think about how to use these as rules that we back out from what we observe in animal behavior, like the circling fish, which we've done, but also in design. So I want to show you how we use these very rules in these different contexts. So first, this idea of adapting a parameter to give us flexibility. So this parameter k theta, right? If I change it, or if the fish are essentially changing something like this as they respond to the environment, this gives them the opportunity to sort of maximize p theta and move in the synchronized way, or just very simply to transition to a circular motion by just changing the sign of this parameter and moving in a circular motion. Likewise, the dancers, right? So we see them moving in polarized ways, and we see them moving in circular ways. Of course, this isn't something that they do consciously, but this is a way for us to understand or to build into these rules for the dancers, for instance, what they do so that these kinds of patterns emerge. So here's an example of what we did in Monterey Bay. So we did these experiments with these, let me show you, see if this works. Yeah, with these beautiful, graceful movers. They're called underwater gliders. They're autonomous vehicles that go in the ocean. They're about 1.5 meters long. They have sensors all over them. And they're essentially just these, what did I do? Mobile sensors that work together. We designed the rules that they follow so that in the ocean, they would move in these patterns, much like those circular patterns you just saw, but in ways, because we had simple ways to parameterize them, we could have them adapt those parameters to change the kinds of patterns they moved in. So there's pretty severe currents going on in this ocean, but what you're looking at this is in 2006, over the course of a month, these 6 underwater gliders that are actually moving up and down, moved in these patterns. You can see who's dancing with whom because of the gray lines, and each one is designated on, there's a color coding between which loop it's supposed to be moving around. But this is a variation of the kinds of patterns you just saw in a very idealized computer simulation. This is what happens when you put them in the ocean and then you allow them to adapt some of those parameters so that they can, in this case, maximize the information that they're collecting in the ocean. That was the idea. This is a 40 kilometer by 25 kilometer by something like 1,000 meter deep volume of the ocean. It's just near Santa Cruz. So this is just north of Monterey Bay. Okay, so that was direction. I just want to say that there's an analogous story with decision making, right? So we talked about motion patterns, but I also tried to justify this idea of how groups also have to make decisions together about where to move or how to move. And so here, instead of sensing direction, we might think about sensing opinions of our neighbors, right? This is a really spectacular story of house hunting honeybees. Something like 10,000 of them move out of the nest when it's overcrowded, and they take their queen with them, and they hang on this, in a swarm on a branch, and something like 300 or 400 go out and scout out cavities in trees, and they have a very well-defined notion of what's an ideal, like a 5-star hotel. It would be something like 40 liters. It would be high off the ground for safety. It has like 15 centimeters squared. Opening should be facing south for warmth, a whole bunch of things. But each bee who's scouted out comes back, and on the vertical part of the swarm does this waggle dance. So it looks like, you saw this, oh, there's a snapshot again, and then here's a little cartoon. With this waggle dance, the angle, it's vibrating its abdomen, the angle relative to the vertical, the gravity, is the angle of the site relative to the sun. It's unbelievable. And the distance to the site, this cavity is proportional to the number of vibrations. And the joyfulness, the sort of excitability of these closed circuits gives a sense of the value, the quality of these sites. Kind of incredible. This was a photo, the one on the right, from Carl von Frisch's Nobel lecture. He won the Nobel Prize for figuring out, decoding this waggle dance. So this is a picture from my lab where we have robots that are moving around in, sort of in theater lights, they're trying to find the highest intensity with sensors on them of green light in this case. So we're showing how you do foraging and search in the ocean, for example, with these wheeled robots. But they're communicating to each other their opinions, and in this case, their estimates of where they think there is a high concentration of stuff. And likewise, in this second project called There Might Be Others is kind of an interesting moment when all of the dancers but one were in one dance module, and they were desperately trying to recruit, much like the honeybees, this one dancer who was trying to be provocative and stick with whatever she was doing. So you see them in a circle, kind of trying their best to get her to join them in what they were doing. Because of the rules, they needed her to join them in order to introduce a new module, which is what they were trying to do. So here's an example in this honeybee story. As I said, suppose there are two nest sites, and they have to choose. But each individual only experiences one or the other. They don't experience all of them. And so the scout, each of them maybe goes to their respective sites. They commit to them. They come back. They do their recruiting. They go back. Hopefully they've recruited some, but if nobody else is there, then they start to lose interest. But if they go back and there are a bunch of them there, even like 25 or 30, and they get this snapshot of a lot of interest, then they actually realize that the group has made a decision by quorum. They realize that enough of them have figured out that this is the best nest site, and they actually come back and they change their signal. They do something called piping, which is a vocalization. And they essentially tell everybody, hey guys, we've decided. So it's by quorum. I don't know, this doesn't work necessarily with people, but they all pick this nest site. And it's kind of spectacular, but almost always they can pick the best out of the sites that they've checked out. And it gets even more interesting because they do this other thing, which is maybe more like people, called stop signaling. It's more like shut up signaling. So when one is committed for A and the other is committed for B, the A will actually headbutt the one dancing for B, right? And that's a snapshot of it. And it has the effect of tempering the dance and getting them to kind of move on with things. And what's wonderful about it is, and they show this in experiment, it allows them to not deliberate forever among near, valuable, near quality options. They actually will flip a coin, which people won't necessarily do. We'll sit there and deliberate, but they will actually flip a coin because they have to. They can't wait there forever. Pretty spectacular. So how do we understand that? And how do we recreate that? And how do we explore that? So let's think about a rule. Here, theta 1 used to be direction. Let's think about it as opinion now. And if it's a positive number, it means I'm for A. If it's a negative number, I'm for B. If it's 0, I don't care, right? So here's the rule. It looks sort of similar to the other one, right? Because we're trying to agree about something now. We were trying to agree about where we move. Now we're trying to agree about a decision between two options. So here's my new opinion, how I change my opinion. This is the rule. And it looks kind of like the sum of these differences between my opinion and my neighbor's opinions, right? If I'm fish number 1, except I'm using U now instead of K theta as my design parameter. It's like that stop signaling. It's the rate of stop signaling. It's how sensitive I am to what my neighbors are telling me. But I also introduced this thing called S, which is it's basically a saturation. It's a cutoff. It says that if you yell, twice as loud, at some point I'm gonna not listen to that extra. I'm gonna just register anything above 1 as just 1, and anything below -1 for the other option as -1. And this is the kinds of things that we can show can happen. These are the kinds of things that can happen with this model, right, which can be used, again, to test hypotheses in nature, to design really interesting, stable, and flexible decision-making in robotics, and explore these things in dance. And so this is a group of, again, 12 agents. Now, 4 of them in the middle have no preference at all coming into this. The ones on the right prefer A, the ones on the left prefer B. The ones on the right and the left don't even communicate with one another. Only the ones in the middle can kind of sense everybody. And here's a picture. The blue are the stable solutions. The red is the unstable solution. And as a function of this dial, this design parameter, what it shows you is the opinion of the group, the average opinion, when that dial is low, like when there's not very much stop signaling, or when there is not very much attention to what my neighbors are doing, will be undecided. But when I crank that up, in this case where the options, I have this kind of symmetry, and half for one and half for the other, I'll flip a coin. Pretty neat. If my preferences are actually stronger, I get this, looks kind of a curvy version of that. But what that means is, as I turn up the dial, in the case on the left, I kind of slowly make a decision, right? If I turn up the dial on the right, I'm undecided, then boom, I make this decision. And if I turn it down, then boom, I turn it off. In fact, you could imagine I might oscillate between these kinds of things. So I want to just draw this to a close by showing you then how we use this kind of collective decision making, both in robotics and I'll show you in dance. And this is a little video that my student Beck Gray made in my lab, one of my labs at Princeton, where again we're using colored, these theater lights. So here I have just 2 robots. One is going to sense the intensity of red, the red robot, and that's going to give it a preference for moving towards option B, which is just the left side of the room. And the green one has a preference for moving to the right side of the room. But they have sort of equal intensity. That's the purple is sort of tuned so that they both kind of have a pull in either direction. But they're using this kind of rule, so they're actually going to stick together. And what we do is take our dial. First, we start low, so they're going to be in that sort of uncommitted state, and then we crank it up so that then they're going to flip a coin, and then we crank it down, and they go back to being uncommitted, and then we're going to crank it up, and they're going to flip a coin. So let me just show you how that works. So now their opinion is the position across the floor. So they do a little dance once they've made an opinion, once they've gotten somewhere. Okay, so remember the green one has the pull towards the blue. It's sort of dragging the red one along, and when they kind of decide on average that they're there, then they do their little dance, which is some task or some activity. Okay, so now we've taken this dial and we've dialed it back down. So now nothing is interesting going on, but now we're going to ramp U back up. And this could be in an environment like it started raining. Oh, we got to make a choice. Or now there's no signal coming from this wreckage after a disaster. So let's just stay at home base until we hear something. And then when we hear something, let's go and check it out together, because we need maybe to use our sensors to explore. Okay, so let me now show you kind of the same idea with our project There Might Be Others. So this is from one of the premiering performances at New York Live Arts in New York from March 2016 with a group of dancers. We actually did this whole decision-making scenario with the musicians too, but that's yet another interesting story. But so here are the dancers. This is just a little clip, and you're going to see them in 2 of the modules. So half of them are going to be doing one and half of them will be doing the other, but there's going to be this kind of slow recruiting, and you're going to see ultimately that all of them are going to join one of them. So this is just sort of one interesting or beautiful moment in this piece. Sorry. So you can see it's pretty distinct here that the ones who are moving very, with very much stillness are in one module, and the other one who are doing this particular series of steps is in the other module. And they get to decide when they want to switch and how they switch, and if they want to join the other. The key here is that one of the rules has to do with how many can be going on at one time. So if we restrict them to only be doing 2 at a time, in order for them to move on and introduce a new one, because there's a catalog of something like 45 of these, dance riffs, dance modules, they have to all come together in order for somebody to introduce a new one. So it's really interesting sort of social dynamics and social decision-making that we explored with the dancers. This is very much a collaborative kind of story. So here they are, having all gathered in the one. So let me then thank you for your attention. I want to acknowledge, in particular, my research groups. I have, this is not all my work. Of course, this is very much a collaborative project, and I have just fabulous students. This includes actually undergraduates, graduate students, and postdocs who, are just marvelous and inspire me every day. For instance, Sophie in the front left is also a theater designer. Standing next to her is Mari, who's a musician. These people bring their full selves to these, and this interdisciplinary space that we live in is incredibly generative. I also want to acknowledge my family, who also inspire me every day and support me. My husband, Tim, is a historian of economic thought. My older daughter, Mara, is a senior at Northwestern. She's an actor. She studies theater and history. And my younger daughter is a freshman at WashU, and she is an artist. She's an art major, but also interested in psychology and neuroscience. So thank you to them, too. And thank you for your attention.